Jai Shri Krishna. Good morning to everyone. On behalf of PG and Research Department of Mathematics, Dwaragadas Govardhan Das Vaishnav College, Chennai, I welcoming you all for the third day National Conference on Contemporary Mathematics and Applications. Let us begin our today's session with a prayer, Tamil Thai followed by college prayer for seeking divine from Almighty God.
நீராறும் கடலொடுத்த நிலமடந்தை கெழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதி சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் மிகுந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
சத்யோரதம் சத்யபரம் த்ரிசத்யம் சத்யஸ்ய யோனிம் நிஹிதம் ச சத்யே சத்யஸ்ய சத்யம் ருதசத்யநேத்ரம் சத்யாத்மகம் த்வாம் சரணம் பிரபன்னாஹ. வாணி குணானுகதனே ஸ்ரவணோ கதாயாம் ஹஸ்தௌ ச கர்மசு மனஸ்தவ பாதயோர்நஹ ஸ்மிருத்யாம் சிரஸ்தவ நிவாச ஜகத் பிரணாமே திருஷ்டிஸ் சதாம் தர்சனேஸ்து பவத்தனூனாம். நமோ பகவதே தஸ்மை கிருஷ்ணாயாத்புத கர்மணே ரூபநாம விபேதேன ஜகத் கிரீடதி யோயதஹ. ஓம் சாந்தி சாந்தி சாந்தி.
It is my pleasure to welcome the resource person of today's session, Dr. C. Vijayalakshmi Ma'am. Dr. C. Vijayalakshmi Ma'am, Associate Professor, Department of Statistics and Applied Mathematics, Central University of Tamil Nadu, Tiruvarur. Ma'am had completed her UG program in Holy Cross College, Bharathidasan University, Trichy. PG program specialized in operation research and computer application from NIT Trichy. Master of Philosophy in Operation Research and PhD in Statistics both from Manoன்மணியம் Sundaranaar University, Tirunelveli, and her PhD thesis entitled on Stochastic Process Bulk Queuing Model and its applications. Ma'am served as a statistician in research and development at Alert Management Consultant, Belgium, Associate Professor in Satyabama University, Professor in VIT University, currently working as Associate Professor in Central University of Tamil Nadu. Ma'am is reviewer of 3 reputed journals. One is Journal of Computational and Applied Mathematics, Elsevier. The second one is the International Journal of Business Information System. Third one is guest editor of International Journal of Computer Aided Engineering and Technology. Ma'am had successfully completed 2 funded projects. One is about 30 lakhs funded received from Satyabama University, and another is about 3 lakhs from VIT University. Ma'am had published 2 patents. Ma'am had received many awards and honors, which are Best Professor Award from Pondicherry Chief Minister, VIT University, Lion Club International, Ratnam Group of Institution, Best Research Award from VIT, Best Teacher Award from Satyabama University, and Bharat Jyoti Award from New Delhi. Ma'am is life member in Indian Society for Probability and Statistics and Academic Council member of VIT Bhopal. Ma'am had published 4 book chapters and she had published more than 115 research articles in various national and international journals. Also presented more than 75 articles in national and international conferences and seminars. Ma'am had published 4 monographs from different publishers. Under her guidance, 15 students have been awarded PhD and she had guided 5 UG PG industrial projects. Ma'am had visited 4 different countries, Singapore, Malaysia, Kuwait, and UAE as an academic visit. Ma'am had delivered more than 85 invited talks as a resource person, and she organized more than 25 programs in various conferences, seminars, and workshops. With this brief introduction, I hand over the session to you, ma'am. Please.
Thank you very much, sir. Am I audible, sir?
Yeah, yes, ma'am. Audible, ma'am.
Okay. If you could just help me out by sharing the screen, can you just give permission, sir?
Start.
A respected and honorable secretary of the esteemed institution, Deji Vaishnav College, Shri Ashok Kumar Guntra, Principal Dr. Santosh Babu, Convener, Professor and Head, Dr. R. Venkatraman, sir, and my all professors of that institute, and other professors from various institutes, my dear students and participants all over the globe. A very warm welcome to all of you. At the outset, I would like to extend my sincere and humble thanks to the organizers for giving me an opportunity to share some of my ideas related to fuzzy and in real-time scenario. And I would like to thank Almighty. In this pandemic situation, everything goes on well. Sir, is my screen visible? Hello, sir. Hello, sir.
Yes, ma'am. It is visible.
Yeah. Sir, is my voice in the correct modulation?
Yes, ma'am. It is clear.
Okay,
Very clear.
fine. Thank you, sir. Thank you so much for your nice introduction, sir. Thank you.
Thank you, ma'am.
So, fuzzy optimization in real-time scenario. Friends, we are all aware about optimization on one side and fuzzy on another side. How are you going to map this, and in what way it's going to help to resolve the vagueness and uncertainty? Even stochastic models help us to resolve it, but it is over a period of time. The decision making always comes over here with respect to fuzzy. So 3 different real-time problems, I'll be in a position to share it and discuss. So to start with, optimization. What is optimization? It is a mathematical discipline. We normally talk about the extreme, that is maxima, minima of functions. So it can be either single objective or it can be multiple objectives subject to set of constraints along with the non-negative restrictions. That is optimization. Normally, when 2 equations of linear type is given to us, 2x plus 3y equal to 5 and 3x plus 5y equal to 6, we know plenty of methods are available to solve and we will get a unique value of x and y. But under this optimization, we could see like the constraints may be of at least, at most, less than or equal to, greater than or equal to, equal to. All these things will help us to analyze such that the unknown parameters x and y can be obtained and those unknown values can be substituted in the original function of optimization. So when we say optimize, it is going to be either maxima or minima. Where we use this optimization? It is used in architecture, nutrition, electrical circuits, economics, transportation, etc. So I can just show some glimpses of applications of this optimization. One application is the aircraft baseline, how it is being designed. What is the main thing as a thing they wanted is like the weight has to be minimized. That is, they take it into engineering perspective as solar radiation. What is the solar radiation? Initially, they have set it up to 350, and once they have implemented the optimization techniques, it has been reduced to 150. That's a great thing. Similarly, the baseline aircraft, with respect to two different parameters. One is the exterior temperature range and another one is the maximum exterior temperature. Both parametric variables are being optimized by using this technique. Another engineering optimization problem is just thrown out over here. That is, we have one system configuration and this system configuration is just displayed over here. When we just compare the first diagram and the second diagram, we could see like some part is missing over there. It is not part actually. They have taken different types of variables like train efficiency, power requirement, energy, cost. All these things have to be optimized in such a way that we get the efficiency of using this in such a way that we have a comparative analysis of the standard configuration system and optimized system configuration. How did they start? What is the thing behind over is like the problem statement and the concept. What concept is involved over there and the detailed design of this particular standard system. Then design validation, analysis and optimization, and manufacturing. And finally, we always try to test it with real-time data and such a way that we can say that our proposed model can be considered to be one of the appropriate model, or we cannot say it is the best, or we can just get the optimal solution over there. The next one, what we can see is like a dam. Construction towards civil engineering, where we optimize the design of the structure with respect to efficiency as well as cost. Normally, when we say optimization, a word comes to our mind, the best. Suppose if we take a boy for this, is this shirt will fit him or not? So it depends on the size and the shape. And here, optimization, it comes to a conclusion that to obtain the best solution, which is going to be a feasible solution. So it is being used in all engineering as well as manufacturing, production industries with respect to production, planning, and control. And in turn, in depth, when we see, even the inventory optimization plays a vital role. And nowadays, the challenging thing is like with respect to supply chain management. Nowadays, this Bitcoin and cryptography has also entered. Cryptography is already existing, but this Bitcoin and blockchain management with respect to optimization technique has been used in all the shares and trade markets also. The basic thing what we need to have it for the necessary and sufficient conditions to optimize is like, as in calculus, we must have come across the necessary condition is the derivative. First derivative is equated to 0, and the sufficient condition is go for the next higher derivatives in such a way that at one context, like it becomes positive and it's going to be the minimum value. On the other hand, if it is negative, it is going to be the maximum value. As a root, I could say like based on the optimization, the root is optimization. It is being classified into many subtrees like continuous, discrete, and very important point to be noted over here is constrained and unconstrained. That is very important. It can be either linear or it can be non-linear also. Some of the curves or the rough surfaces when we see like manufacturing a lathe, or if you just go into the manufacturing industry, they always try to have a non-linear curve like x cube plus x1, x2 square. You can have n number of variables to be introduced and subject to n number of constraints also. So it can be either unconstrained or constrained. Under unconstrained, we can solve it with respect to different types of techniques available, non-differential optimization, non-linear least squares, etc. Under constraint, we have linear programming, which we have come across like, a non-linear constraint and bounded constraint, and you can have network programming, stochastic programming, etc. The integer programming and stochastic programming is once again under the discrete state it comes out. So when we talk about this, a model solution for this, we try to read the problem statement, design a model, and apply the different types of tools over here, analyze what type of variables. It can be a decision variable, it can be a controlled variable, it can be a Boolean, anything it can be like. So we just try to analyze that, then fit a model over there and try to find a solution using any types of software. Just we can have design a model, an analytical model will always help us to get the optimal solution. So I can just give you another 3 examples over here, where in real-time scenario, Kellogg's, the great cereal producer in the world, has used the production and inventory and distribution, which made them to save $4.5 in the year 1995. Another great company, Procter & Gamble, is a consumer goods company, and they have implemented integer programming techniques and network optimization are based on the GIS, that is Geographical Information System, and they could save more than $200 per year. That's a great thing for them. Then the third one is, I would have come across a great computer company like, that is Hewlett Packard, that is HP company. They have used the advanced inventory optimization techniques, could save like that. Now, we move on to fuzzy set. Friends, as we are all aware about this, and you must be more confident by listening to so many lectures of eminent persons, but a small run through over here. When X is a collection of objects within X like, then we try to make it as a second point of ordered pairs, and 4 different notations are there, like the set notation, what is the topic variable, what is the generic element, and what about the membership function over that, which is belonging to that X. And what are the different types of operators we can just over here is from the slice, of which we can use it as a membership function from the slice of this, or the join, or we can use it as a complement. So different operations are being displayed over here. Now we move on to the multi-objective linear programming. What is this multi-objective linear programming? How are we going to resolve this? So we would have seen like single objective, just we want to get profit, maximize the profit, at the same time minimize the cost. But this is going to be a multi-objectives, and how we are going to describe the objective function, then set of constraints. Along with that, it is going to be whether single or multiple. Now, case 1, when it is going to be a single objective, if C is the cost and Xi is going to be a variable, a decision variable over there, and the product of this with respect to n number of variables, we have to minimize it. That is our objective function. Subject to one constraint, that is, it can be Aij, Xij less than or equal to Bi. And what is this Bi? Bi is the available resources in our company. Suppose my left hand side is, I'm manufacturing 3 different types of products, X1, X2 and X3. I try to say that 3X1 plus 4X2 plus 5X3, 3 times of the first product, 4 times of the second product, and 6 times of the third product should be less than or equal to 100. If this 100 is a time constraint, I make it as 100 hours. So what does that meaning? It is understood that within the stipulated time of 100 hours, I should be in a position to manufacture these 3 different types of products. That is the base of a single objective function. Now, when we move on to a multiple objective function, we treat it as a vector in such a way that that vector consists of n tuples, that is x1, x2, etc., xn, in which case we can minimize that function which contains more than 1 or 2 objectives and with n number of variables and m number of constraints. Then we try to say that it can be either minimize the time, maximize the profit, then efficiency, like that. You can have n number of objectives with n number of constraints and variables. Now, moving on to the real-time scenario problem, where we have the TSP, traveling salesman problem. I think we are all very much familiar and you are all legend on that particular topic, like where we try to find out the cost, which is minimized by transporting m number of sources to n number of destinations. That is the basic of traveling salesman problem. So that is mainly dependent on my supply and demand. Now, just we go in depth and try to apply this fuzzy in such a way that we will be in a position to get the optimized route along with 3 different parameters. One can be either time or cost or distance. So here, the basic variables which has been used here are n number of cities. What is Dij? I and j are from the distance from city I to city j, maybe from Chennai to Tiruvallur. and decision. We treat this xij as a decision variable, which can be considered as a Boolean also. If you can go from ith city to jth, or from jth city to I, and if it is connected, then we try to give 1. If not, we give it as 0. So here in this context, the general formula or general basic mathematical formulation is defined over here as like that distance, product of the distance and their exister transition from ith node to jth node, that this has to be minimized with set of constraints given as Boolean 0 and 1, where xij for I and j variable, it should be equal to 1. And this, why it has been defined over here is like the coefficient of dij is always the distance from that I city to j city. And the second one, decision variable. When we just consider this decision variable, if that xij equal to 1, it is understood there exists a route from this to this. Meanwhile, if you don't have a transition or if you don't have a route, then we say it is that Boolean is going to be 0. The first constraint function, summation xij equal to 1, if we consider that, it is understood that every place is the starting point of a tour to a destination. The second constraint, where I is the variable over there, it is defined every place is a destination of a tour from the starting point. So when we move on to fuzzy linear programming, we are trying to combine this fuzzy and optimization on 2 different contexts. That is optimization under fuzzy environment and how many objective functions can be maximized or minimized or optimized can be k number of optimized functions, and this has to be minimized with respect to some decision variables. So this is considered to be a multi-objective fuzzy linear programming. So in this context, we have maximum of one thing and minimum of another thing. What is this zk and zm? They are the objective functions, 2 objective functions which comes under the case of multi-objective, subject to 1 constraint and non-negative restrictions. That is very, very important. Now, this x as a vector, what does it contain? As already discussed, it has got n tuples, which is on the real space of R power n. And this is considered to be a decision variable. Now, we consider that the objective functions and the constraints are fuzzy, then the model can be of the form like the objective function should be greater than or equal to some variable. What is that? We call that as an aspiration level. Where does that aspiration level come? It is from the nature of destination. Similarly, another thing we want to have it is another aspiration level. Here, we try to have at least and at most 2 different things and subject to the constraints to be, and that constraint always help us to analyze whether it is at least or at most. At least is a relational operator greater than or equal to, and at most is less than or equal to. Sometimes we can have equal to also. And when we have in ordinary linear programming, the relational operators constraints, we try to solve it by 2-phase method, big M method, revise, all these things we try to do. Now, the problem is over here, it is a little bit complicated to understand the final discussion or conclusion or decision to be made on uncertainty. That is the problem here. So the next step is going to be, how are we going to have the decision set for this fuzzy? And this is going to be based on the aspiration level. So friends, we all know the decision set theory is always defined as the minimum of all these membership functions. So here we have got 3 different types of membership function. It is always related to the destination. And the third one, what we talk about, the first 2 one are the aspiration, that is with respect to membership function destination. The third one is with respect to the membership function of constraints. So when we want to optimize this of aspiration level, first we have to find out the aspiration level and tolerance. So how are we going to do this? So here we try to find out the optimal solution, feasible solution, by having it as min, max, min, that principle, where x is always considered to be positive, and that is going to be the fuzzy set, a single fuzzy set, which is a combination of 2 membership functions and 1 function of constraints. Now, how to implement this appropriate membership function? The third step goes like this. For instance, if we have some constants like Tk and Tm may be related to the time or distance or cost, whatever it may be like. How can it tolerate this? What is the meaning of this tolerators? I have some level I can tolerate. After that, I may burst out. This is the verbal language we say here. But here, the toleration is always such a way that it is disobeying from each and every objective function and constraint. Is it deviating from that? So the membership functions for this particular objective function, as you must have come across, like how we try to define it, that is mu is z k of x, where it is under the level, in between the range, and greater than. So it is subdivided into three classifications of 0 and 1, and 1 minus those things what we had it over here in the previous, where zk and this zk of z0 and zk of x is going to be my objective function. The next one is, this is my objective function. The second one is also defined in the same way to Tm. And the third one is for the constraint. The constraint, if I have it as g of x less than or equal to bi, I can rewrite it as g of x minus bi equal to something. Here, 1 minus, by using the complementary operator, 1 minus of that, the ratio of the deviation of the constraint with respect to time parameter is defined as a membership function for the constraint. Like that, we can define it for n number of constraints. The next one is, we go in for the degree of x. What is this degree of x? Is always the minimum value, which is defined as an alpha. This alpha is ranging from 0 to 1, such a way that the maximum and minimum of numbers, it tries to say that bounds. In calculus, we try to say it as a bound or limits, upper limit, lower limit. Here also, two extreme conditions are there over here. So for the constraints, now objective function, we know how to define it. For the constraints, how can we do it? That is, we try to take this alpha to be the minimum in such a way that that will be less than or equal to the fuzzy converted objective function and constraint. First two are objective functions, fuzzy converted. The third based on the membership function, and the third one is the constraint. And finally, xij is positive, which is non-negative restriction. Now, what is the base we have to enter into traveling salesman problem for solving it? That is, we have to find the optimal route. There are so many algorithms like Dijkstra's algorithm, Kruskal algorithm, Prim's algorithm to find out the shortest route from source to destination, which will be the shortest path based on the distance or weights from one node to another node, from one place to another place. But here, the idea is the optimal route to travel all the cities, and so that the cost has to be minimized. And what will be the decision I need to get it for this with respect to three different things, that is cost, time, and distance. So how do I define this decision variable xij? I try to say that the position of I is just tending to position of j, then give it as 1, otherwise 0. So here, three things we have made it. One is, the first one is, we want to travel from ith city to jth city. Then think about the cost, that is. So the cost is always the link, sum of the link including the route. And second one is the aspiration level for the objective function on cost, which has to be minimized. And the third one is the tolerance level T1, till which level I can tolerate it, in such a way that the first objective function is listed over here as Z1. It's a product of the cost and the variable, decision variable, which has to be less than or equal to first aspiration level Z1 naught. And what is Dij? Dij is the distance which has been taken over from this ith to jth city. Now we move on to the second one, second objective function, Z2. This Z2 is once again Dij. This is first one is cost and second one is distance. The product of the distance from ith to jth into xij should be less than or equal to my aspiration, that is level. The third one, we move on to time. How much of time we have spent from this particular node or vertex from particular place to another place is being discussed over here. That is Z3 naught is the third tolerance level, and this is going to be how the objective functions are defined. And very, very important point is how to get this aspiration level? The aspiration level on objective function is always calculated or determined based on solving each and every objective function by having a small word of obstacles on traveling salesman problem. Normally, we try to say obstacle is like when we just go and something is crossing, we wait for it like that. That is not the case over here. There is a limitation over here, like how? The reason is the neighborhood cities has to be visited. That is also one point here. So we try to express this as the constraint as we say, like in probability, the summation pi equal to 1, sum of all the probabilistic values equal to 1, like that. Here also we try to have summation I equal to 1 to n, and similarly j variable, and it should be equal to 1. That means a particular route. Suppose if I'm traveling from Tiruvallur to Chennai, I just go via Pondicherry, Chidambaram, like that. I take this ECR route, and if that is the case, that route cannot be selected once again. That is why we try to fit it as the route which is going from I to j and j to I should be the sum of these two things should be less than or equal to 1 is one constraint. The second thing is like it's always going to be greater than or equal to 0. And third one is if we have a route existing from one place to another place that is equal to 1 is the third one. Now, so how to get this aspiration level as we discussed over here is going to be based on solving each objective function. And how to get the tolerance level? The tolerance level is like take one objective function, first objective function cost. That is find the difference between the coefficients of each and every objective for a selected route, that is max value minus min value will always give us the tolerance, right? Now, let us go into the real-time problem, that is fuzzy optimization model for a real-time multiple traveling salesman problem. So what is this? It is going to be defined as a single depot and multiple depot problems. And this multiple depot problem, what is that? Is like it starts and it ends in various depots. That means it doesn't have a single server. But single depot problem is start from one place, say Tiruvallur, come back to Tiruvallur. That is the idea. So what we have proposed over here in real-time scenario of a fuzzy optimization model is the new model has been designed with single depot and fixed destination. And this is solved with fuzzy linear programming by converting the multiple TSP into TSP. So initially we have some assumptions and we have taken the real-time data to solve this and fixed destination with fixed salesman into the fuzzy model. And what are the three different parameters normally we can do it? Time, cost, and distance. Now, in this particular problem, we have taken the distance and cost as the objectives to start with. So, at random, we have chosen 4 salesmen starts the travel from home station to fixed destination. How do we made it like this cities how we have to go? We have numbered it as 1, 2, 3, 4 and end the journey to the home station. The second salesman, next, see the cities have been named it, but we have given a number to each and every city and the real route has been taken from Google. The third salesman has to visit another 4 set of cities and come back to the home station. Like that, it is given over here. And what we decide about the parameters and variables. So what are the different types of parameters and variables we can have? One is the traveling distance from one city to another. Here, it is made it as ith city to jth city. Next one, how much of cost incurred from ith city to jth city? For this distance and cost, we have to fix the aspiration level. That is very, very important. So at the same time, we know how to calculate this aspiration level and tolerance level, which has been already discussed. Now, for this distance and cost, once again, we have to calculate the tolerance level. These are the basic parameters and variables which we have to take into account. Suppose if we include the time also one more parametric variable over here, like then we can say as TTIJ. For this time traveling from one city to another city, we have to find or obtain the aspiration level and tolerance level. Okay, fine. So what is a mathematical modulation? That is already we have just seen the general format. The same way we have just found we have framed the objective function for total distance, objective function for total cost. where Xij is going to be a Boolean variable. Now, take the real-time data we want to have it like, and we made a matrix, and this matrix consists of the number of cities and wherein the distance and time is made as an ordered pair. That is the distance. Suppose if I say like 0, 0, they are in the same city like, so it all the principal diagonal elements does not contain any values because they are not moving from source to destination. But when we take the 0 to 1, they have started from 0 city, they have reached to 1 city, and the distance is 33 kilometers and the cost is 297. So the real data has been taken out, and this is for each pair of cities it has been done. Now, this is for the first salesman. Similarly, for the second salesman, it is done, and for the third salesman, it is being framed as a matrix with respect to traveling distance and the cost. And fourth salesman also, the distance and the cost which has been included over here. That's nice. So now we know the distance and the cost involved for the 4 different salesmen who is going to travel based on the routes given to them. So based on the initial suggestion, like we have obtained the aspiration level as 120 and 1119, and the tolerances we got it by deducting from the coefficient 5 and 6. So first set of cities, second set of cities, third set and fourth set by various 4 salesmen, the aspiration level and the tolerances are obtained based on the previous construction, how it was discussed. Now we construct the objective functions for 2 things. One is based on the cost, another one is based on the distance with the tolerance level. And what is this 33? What is the meaning of this 33, 40? All these coefficients, I can just show it based on the confusion matrix, what we had it. 33, 40, 52, 61. And this like this. What is the 0, 1? From 0 city to 1 city. Like that, the routing has been made, and this is going to be, 1 minute. This is less than or equal to 120. What is this 120? The aspiration level. According to our general optimization problem in LPP, we try to say that AX is less than or equal to B. You have a coefficient matrix, X is the unknown variable, and X can contain n number of variables. Less than or equal to BI is my available resources. This available resources is directly related to the aspiration level, that is target level, maybe we can say. So 2 different objective functions have been framed over here based on the tolerance and aspiration level. Now we convert this into a fuzzy optimization model such a way that based on the membership function, we try to have it. Then rest of the routes, how it will be the possible routes for each and every salesman. And this is going to be, at most, it should be equal to less than or equal to 1. And finally, we have the non-negative restrictions for 2 parameters. One is Xij, another one is alpha. This alpha range should be between 0 and 1, which we have to obtain while we find out the optimized route. So similarly, for the second salesman, based on the matrix and the route, what is the 0 to 5? This is the coefficient, and this is ith source, this is jth destination. With respect to the aspiration level as BI and tolerance, it is being framed. Then convert this using membership function and such that my alpha should be less than or equal to the complement of the first one, membership, and the second one. The rest are for the all these are the root conditions which satisfy, and it should be equal to 1 exactly. And some other things will be less than or equal to 1 because the reachability is very slow. And this mathematical model, and when we say it is going to be for the third salesman, we just go to the matrix. And for the third salesman also, this is being discussed like this. And we convert this optimization model into a fuzzy optimization for the third salesman with respect to the membership function and the root conditions. Similarly, we can go for the fourth salesman, how all these 48, 28 are the coefficients are being from the matrix. It's related to distance is the first objective function, Cost is the second objective function along with the tolerance level and aspiration level. So it is converted into fuzzy in nature. And now we have solved this problem using MATLAB. And when we solved it, we could see like for the first salesman, for the first salesman, we could identify the time along with the second two objective functions were there. One is with respect to distance, another one is with respect to cost, and alpha also we obtained it, that is 0.6, and the optimal route over here, because there was some uncertainty or vagueness over there, like which has been eliminated or eradicated. So optimal route is like 0 to 1, 1 to 3, 3 to 4, like that, in which the solution is optimized for that particular salesman. Similarly, we could be able to get the values of objective function with respect to cost and distance. And the alpha over here is 1. It is in the extreme end, and we cannot really say that it is going to be the best optimal solution. But when alpha takes a value 1, then the optimal route has been obtained like this. For the salesman 3, it is going to be the optimal route, and for salesman 4, this is going to be the optimal route. Now, we are able to find out the optimal routes and the optimized value with respect to distance and time. So the optimized traveling distance is 522 kilometers and the cost is 4,698. Now, when we just compared it with the real, where we got the real-time data, we could see like we have optimized it, the distance, like they were telling it around 680 kilometers. Here it has been reduced to 522 kilometers, and the cost they were telling around 5,000 rupees and odd, and here it has been reduced to. So here we could minimize the distance and the traveling cost based on the fuzzy optimization model. So this is how we did it. Like the background scenario is like drawing a network between 0 and 4 cities, 0 to 8 cities. Then we keep on updating the number of cities 0 to 16 cities, in which without having any link, like cross link. So we were able to get the optimized one. So here a fuzzy optimization model is framed in such a way that it is modified as a traveling salesman problem and solved using fuzzy multiple objective function. And two parameters are being optimized, minimized, that is distance and cost. Now, friends, we can extend this concept by having one more thing as like time, distance, cost, and time. Any more parameter you want to do it along this traveling salesman problem, that is also possible. The same concept has been extended with respect to real-time mission planning with unmanned aerial vehicles. Friends, you must have seen like it's like a robo control, where when it is unmanned means we do not know who is operating it, how it just moves out. And this real-time application is used in Navy, Army, and Air Force to just shoot that particular target. Instead of the salesman, we have just taken it as an unmanned aerial vehicle. So here, this unmanned aerial vehicle is mainly used for applications to collect data from different types of targets. And it is used in military, as I said, like border, patrol, warehouse, and automation. So this, how it is like UAV, unmanned aerial vehicle. We need to identify the series of locations which has to be visited and train the machine in such a way that it goes like a robo and visited and it just come back to the home station. So the same thing we have done it over here. Only difference is fixing the targets, optimizing the distance and time. Instead of cost, we want to see distance and time, how it works for this unmanned aerial vehicle. The reason is when you have the distance along with time, that is more efficient rather than the cost. The cost will be always included over here when you try to travel. But at the same time, the construction of that robo or unmanned aerial vehicle, which is going to travel, that is a hardware part. So we try to take it from base one and fix the targets at each and every place. Try to check it just reaches to the home station. So what are, so here like 4 salesmen, here we have the unmanned aerial vehicle, which is, we have named it as alphabet, that is going to be the target. So the target has to come back to the base one. So the distance and time along with the aspiration level and tolerance level are set. And we have constructed the objective functions with respect to distance and time. And the how we have solved it as an algorithm is like the defining the objectives is going to be in terms of trapezoidal numbers, and it is with linguistic variables. And we have used alpha cuts using the membership function. And the ranking, we have taken this Yargis ranking method, and we have solved this fuzzy multiple objective function with ranking matrix. So when it is going to be like that, what are the different types of linguistic variables we have taken? One is very small, small, medium, above medium, large, and very large, like that, because we had to attack the targets. The trapezoidal fuzzy numbers for the distance and time, we have given it over here. And this is the real-time data. And the matrix, it has been represented with respect to the target and linguistic variables. This is the idea over here. That means A to B means yes. What does it? Yes, yes means small. And A to C is large. So when we just see that the target where it is located, based on that, using this linguistic variable, it is being identified as a matrix. Now, this matrix, we just move on to the next part for fuzzy membership function for distance and time. We know how to construct fuzzy membership function for this, and this is going to be with respect to different linguistic variables. We have done it. And what is the 714, all these things? These are the things which we could see it from the trapezoidal fuzzy numbers. So once this is done for the first unmanned aerial vehicle related to distance and time, that is with respect to all the membership functions are defined based on that fuzzy numbers. And we move on to alpha cuts. When we use alpha cuts for Yargis ranking method, then we could be able to get the time, how much, based on the distance. And the ranking matrix is displayed over here with respect to among the targets. That is going to be, you may have n number of targets, which target has to be shoot, right? So we convert this to a mathematical model based on our aspiration level is our right hand side of the thing, and the tolerance level has been calculated using the coefficients of the matrix. And once this is done, then we are converting into fuzzy linear programming based on the linguistic variables, and instead of roots, we have the targets. And this is being constructed. And similarly, we do it for the second unmanned aerial vehicle. Membership functions are constructed, and alpha cuts and Yargis ranking method is implemented for the second UAV. Ranking matrix has been constructed, and it is converted into a fuzzy model. And third UAV, the same set of linguistic variables, the trapezoidal fuzzy numbers for the distance and time are different. Based on this, we have constructed the matrix representation of the targets only with respect to linguistic variables, and the membership functions for the two parametric variables, distance and time, are being covered. And we have found the alpha cuts for distance and time using Yargis ranking method. And we just move on to the alpha cuts for the distance and time as a matrix, because based on this only, we can find out our tolerance level and aspiration level and convert it into a linear programming problem. And once it is converted, then it is converted into fuzzy linear programming. What is our objective? To maximize alpha. Similarly, for the fourth UAV, this is being done, and matrix representation, membership functions, and alpha cuts for the distance and time. And along with that, the mathematical model formulation based on the aspiration level. And this is going to be two objective functions. One is with respect to distance and time, and convert this problem into a fuzzy based on the right side. If you see, alpha is going to be first objective, and second alpha is going to be the second objective. Rest are all the constraints based on how it is being targeted. And finally, when you solve this particular problem, the numerical solution is being given over here is the optimized distance, optimized time, and alpha value, and via which route has to be considered to attack the target. This is for the first UAV and the second UAV and third UAV. So overall, the optimized value, when we see it like, it is going to be the distance and time. It is reduced like a salesman traveling. Here it is going to be a mission. So a mathematical formulation for a mission planning is designed over here. And this can be used for semi-automatic also, which we have not checked it so far. Like, but the only thing is like, is it going to be a single depot or a multiple depot? And at the same time, single target or multiple target. That is the idea over here. Now, we move on to the third application. This is a very good real-time scenario application. All these things are already published by us. Like, and what is this is like emergency medical service system. Now, what is this medical system? So whenever we cross, when I crossed via any road, I could see like so many ambulances are flying off like that, where we try to stop somewhere and leave way for them. But this is going to be, I felt it, we felt it as, it's going to be a fuzzy environment. So we want to design an emergency medical service system. Under what conditions? The accident happens in one place, there will be a server or a home place where they try to send the ambulance to that incident point. And from that incident point, it reaches to the neighborhood places hospital. In the hospital, the treatment can be given based on the severity condition of the patient. From there, it just goes back to that. In between, there are chances like if you are able to have two different accidents happening in the same place, what kind of rerouting algorithm can be given over here? How are we going to optimize our route and the distance for that driver to reach the destination in such a way that the patient life can be saved? That is the idea behind. So the efficiency is always towards public safety. We have designed this model, and here to minimize the adverse controls like. So what are the problems we face it over here? Loss of property, that is with respect to the response time to incidents. When the call has been received, but there was no vehicle in the home station to be routed to the particular place, then what happens is like, we may lose that particular person. That is one case. The second case is like the ambulance driver takes a shortest route from the home station and reaches that particular incident state. There are chances due to traffic congestion, he may not be in a position to reach that particular place. If that is the case, what will we do like that? So is there any chances to have a rerouting in such a way that another shortest route, which is not being available in the GIS system or Google doesn't help us, like Google Map doesn't help us in that case, then how to optimize our parameters of time, distance, right? So this emergency medical system will help us to dispatch different types of strategies for the travel time. And what are the basic characteristics we have it over here? And this help us to have route diversion is one point. And suppose something happens to the ambulance driver or something like that, can I just have a reassignment some person in such a way that which is not considered in the so far literature survey of the existing models? We want to include that also. A proper route diversion, it should not become a joke like because it is life, it is safety. So the route diversion or reassignment will always help us to improve the performance, because if there is a severe traffic congestion or severe incidents happen. So what are the characteristics of this emergency instance? One is severity, time intervals, that is between home station to incident, incident to hospital, hospital to any other place, then like that. So arrival rate, location, detection time, response time. On the scene, can we just give any first aid treatment? If not, what should be done like? That is also very important. The response time, the minute we receive a call in the home station that some accident has happened from any police bureau or from any public or anything like that, the response time has to be minimized. That doesn't happen normally. So what is the need for hospital treatment distribution? So this EMS vehicle is based on two characteristics. One is location, another one is destination or route. We try to frame some rules like based on the current status, that is waiting for the command from home station, moving to the incident point, staying on the scene. There are chances if it is going to be minor to be treated, then come back to the home station or transport the patient to a hospital, stay in the hospital for some time because doctors may say that this cannot be done over here, take it to another hospital and moving back to home station. We framed rules for dispatch strategy like, and what are the different types of destination changes, vehicle changes, drivers should not change the route, and these rules help us to go for the reassignment and routing change. And the flow diagram for this is like based on the traffic generation and incident. Incident means accident, incident generation. This is how it has been designed. The vehicle information should be there in the home station. Otherwise, it's very difficult to make a move or a transition from one state. So consider this as a traveling salesman problem from one place to another place, from this incident to the hospital, hospital to some other place, like that. So the mathematical model we have used over here is we have designed the dynamic shortest path algorithm and dispatching decision by using first. So how we have formulated this is like, our objective was minimize the response time subject to many constraints. The first constraint was vehicle information. We should know the total number of vehicles. Is it staying there idle, or it has moved out of the home station, moving to the incident point, staying at specific points to deal the accidents or incidents, leaving to hospital from that and staying to the hospital. And next is incident. And we have to wait, if not reroute that ambulance to take care of that, because if there is no treatment needed to be taken to the hospital, that ambulance has to be rerouted for some other incidents. So incidents which has been treated by the government and priority has to be given. Hospital, vehicle, and is it going to be two-wheeler or four-wheeler, like that? Dispatch to the incident point, dispatch to the hospital, back station. And time. Our objective was to minimize the response time for each and every incident. And the predicted time is very, very important from home station to that place where accident has happened. The incident to that is also important. What are the different types of constraints? We can improvise and make it as a challenge by including more constraints also. That's always possible. So vehicle constraint, position, dispatch constraint, and one incident of rerouting, destination change. Somebody would have told like it has happened in Chennai near Vaishnav, but it would have happened in OMR also. Right? Waiting constraint, reduced traveling time. So what are the different types of parameters we have taken over here with respect to time is the travel time from incident, waiting for treatment, time to hospital, time to home station. Then aspiration level, one is with respect to traveling time, and this is with respect to the incident and hospital and home station. And the tolerance level and the aspiration levels are set or obtained. It's not set, it is obtained. And design the mathematical fuzzy optimization model with respect to travel time to incident and travel time to hospitals and travel time to home station. This looks like typical of cost, time, and distance. Once it is done, the constraints are set. The constraint is always like the EMS vehicle, the ambulance, the destination should be either to the place, or it has to be the hospital, or it has to be the home station. The sum of all these things should be equal to 1. Other things that it's going to be the travel time whose destination should be incident and hospital, and that should be always positive. The next constraint is going to be with respect to the time of EMS vehicle, the destination. And here also the destination could be from the home station or waiting for treatment where you have reached the hospital. Then we move on to the next thing where each vehicle should go to that particular place for treatment. And is it after finishing the task, like how much of time it has taken for each vehicle should reach the home station after completing all the tasks. And now these are the notations which you have used in this particular problem of designing a fuzzy optimization problem. And we have taken the real-time data from Chennai, and this is like 4 EMS vehicles are there, 3 incidents happened. And this is time in minutes among EMS vehicle and incident, 4 EMS with 2 hospitals, 4 EMS with 1 home station. Once we have taken the real-time data, the aspiration levels are obtained, the tolerance levels are obtained. Convert this into a fuzzy multilinear programming problem based on the coefficient matrix which we have it over there with respect to time and distance, and the tolerance levels and the aspiration. Aspiration level is on the right hand side of my objective function, which is going to be like the resources which has to be completely used over that. Beyond 280, I cannot do it. So the availability of this particular route for the first objective function has to be taken over within 280. Membership functions, triangular membership function has been designed for each and every variable, that is Z1, Z2, Z3. And it has been, these things have been converted into a fuzzy linear programming problem by using max-min approach. This is typical of, it should be Cx is greater than or equal to alpha. That should be greater than or equal to in such a way that we will be in a position to find that alpha value perfectly. The first three are with respect to the membership functions. The later on is like how it is being routed via what, which is equal to 1. So we are having 101 constraints for this. So when we solved this problem by using MATLAB, we could see like for the first objective function, it is 292, second objective function 245, and third variable, it is 496. The overall reduced response time is 1034 minutes, but the reduced time based on the aspiration level given by the real-time data people was 1075. So we could just justify saying that our response time, a minimum of 40 minutes, have been reduced in such a way that the safety can be ensured. So we wanted to make a comparative analysis with so many alpha levels, the duration of occurrences waiting for treatment with respect to different types of alpha level, which is on the acceptance level, and we could identify that ours can be considered to be one of the appropriate model for this current scenario. So this newly designed model helped us to have a different type of dispatch strategy, and it's going to be a real-time one. And this real-time data has been used over here in spite of the traffic congestion. And one very important point is rerouting algorithm has been used over here. And this mathematical model, what has been designed over here, and like traditional QU models, doesn't allow the route diversion. Our model can allow the route diversion, and rerouting also is possible. So when severe accidents or incidents happen in any place, this can automatically handle more timely fashion, and it can help the society to be on safer hands. Thank you.
Thank you, ma'am.
Thank you, sir.
Thank you, ma'am.
Thank you, sir.
This wonderful session.
Thank you, sir.
Now the time to questioner is any question? Any questions? If no questions, we can conclude this session.
Sir, I would like to extend my sincere and humble thanks. A sincere thanks to Almighty and humble thanks to the organizers of this national conference on contemporary mathematics and applications. Once again, my thanks to Almighty, because there was no power cut. Normally, we used to have power cut in Tiruvallur, right? So thanks to Almighty for sharing some of my ideas. This is going to be an initial start, according to me. Your views and queries or suggestions are always welcome to move forward. And once again, my sincere thanks to all the organizers, department faculty members, higher competent authorities, secretary sir, principal sir, and the convener of this program, Dr. R. Venkatraman sir, and my dear participants. Stay safe, stay blessed. Thank you very much.
Thank you. Now it's time for vote of thanks. I'm very happy to propose my sincere thanks to the resource person, Dr. C. Vijayalakshmi, Associate Professor, Department of Statistics and Applied Mathematics, Central University of Tamil Nadu, Tiruvallur, for enlightening the session with a fuzzy optimization in a real-time scenario. Really, it is a remarkable session, ma'am. Thank you very much for accepting our invitation for this 4 days national conference on contemporary mathematics and applications. Last but not the least, I would like to thank the beloved participants for their participations. Thank you all.
Thank you very much, sir.
Next session.
Shall I leave, sir?
10:45. Yes, ma'am, you can leave, please.
Thank you very much. Thank you all, dear participants, and thank you, students. I could see so many students over here. Thank you all, students.
Thank you, ma'am.
Yes, good morning. So, second session is rescheduled for today's 3:30 to 4:30. As a Dr. Kushumdeep ma'am, program will start by 3:30 to 4:30. Now the next session will begin by 12 o'clock.